So in question 1, you're given the structure of an ester, you're asked which statement is most likely to be true. So I've just written out the molecular formula of my ester and I've calculated the formula mass, which is 88. This information is just going to be helpful when we're looking at these statements. So if we look at the first sentence, the peak at MZ45 is due to this fragment. So they've given me a fragment. The first thing I want to do is see if it's possible to get this fragment. Okay, so I've got 2 carbons, 5 hydrogens and 1 oxygen. Can I break this molecule apart and end up with this fragment? Okay, so if I were to break this bond right here, I would be left with 2 carbons, 5 hydrogens and 1 oxygen. So I can break this molecule apart and be left with a fragment C2H5O. Okay, does this fragment have the molecular mass 45? 2 times 12 plus 5 plus 16 is 45. So this statement here, A, seems to be true. So my first instinct would be the very first statement, A, would be true and will be my answer. But to confirm, we can look at the other statements and make sure that they are not true. So the second statement says the peak at 44 is due to the fragment C3H8. So again, I'm going to look and see if it's possible to get a fragment with 3 carbons and 8 hydrogens. Okay. Now we do have 4 carbons in the molecule, but you'll see that they are separated by an oxygen. It's not possible to have a fragment with 3 carbons that doesn't contain any oxygens because those 2 carbons are separated by the oxygen in the middle. So this fragment is not possible. Therefore, I know B is not going to be true. C, the peak at MZ88 is the M+1 peak. Okay, we have seen that the molecular mass of the entire molecule is 88. Okay, so that's its molecular ion peak. The M+1 peak would be because of the small proportion of carbon-13 atoms, and the M+1 peak would be 89. So if the formula mass of the whole molecule is 88, the M+1 peak is going to be 89. So this statement here is incorrect. It's not true. And then it says there is no peak at 43. Okay, I've worked out that the formula mass of the entire molecule is 88. Okay, we saw that this portion of the molecule here, from the first part, had a formula mass of 45, which means that this part of the molecule here is going to have a formula mass of 43. Okay, those 2 fragments taken together will give me my mass of 88. So when they say there's no peak at 43, that is incorrect. This part of the molecule here will give you a peak at 43, and this is a likely to occur because we know this bond here can break. Okay, if this bond breaks and the positive ion stays with this fragment, you are going to have a peak at 43. So B, C, and D are all incorrect, which means A is your statement that is likely to be true. In question 2, you're asked which alcohol is not likely to have a fragment with a mass of 43 in its mass spec. Okay, so I think the easiest thing to do is to work out what fragment will give you a mass of 43. The way I do this is it's an alcohol. Okay, so you know you've got carbons, you know you've got hydrogens, you know you've got an oxygen in there. Okay. Carbon has a mass of 12, so if I take 43 and divide it by 12, I can see that I've got a maximum of 3 carbons in there. Okay, 3 12s are 36, so the maximum number of carbons I can have in there is 3. And if I take 3 carbons, so 3 12s are 36, I've got 7 left over, which means I could have 7 hydrogens. So C3H7 is a common fragment, it's a propyl fragment, and it's got the mass of 43. Okay, you might then ask yourself, it's an alcohol, is there any other way that I could get a mass of 43 in a fragment? Well, we know alcohols have oxygen, okay, they've all got the OH group. So what I also did was I did 43 minus 17. Okay, that 17 is coming from the mass of an OH group. 16 for oxygen, 1 for hydrogen. If you do 43 minus 17, you get a mass of 26 left over, okay? 26 divided by 12 tells me if I had 26 left over, the max I could have there would be 2 carbons. That would give me a mass of 24, and that would also leave me with 2 hydrogens. So if I were to include the OH in my fragment, a likely fragment would be C2H2OH. Now, this is not a very common fragment, okay? It's not going to be a simple break one bond and get a fragment with C2H2OH, okay? So this fragment here would be incredibly unlikely especially at A level, you'd have to break multiple bonds to end up with a fragment like this, whereas C3H7 would be a very common fragment. So I'm now going to look at my different molecules and see if any of them have a C3H7 that I can easily break off as a fragment. Okay, I'm going to start with A. Okay, I've drawn out A to make it easier to see. And if we come down here and look, right, you've got 4 carbons, but can I cut off 3 carbons and 7 hydrogens? So if I go 1, 2, there's 3 carbons, okay? If I were to break off this bond here, I'd still be left with 4 carbons. If I wanted to break off, if I say I broke this bond and this bond, so I decided to break this bond and then had a second bond break there, I would end up with 1, 2, 3 carbons and only 6 hydrogens. So even breaking 2 bonds, I still don't end up with 3 carbons and 7 hydrogens. So I'm not getting that C3H7 no matter which bonds I break. And you can try and break all the different bonds. You're not going to end up with C3H7. If we look at B, I don't even need to draw it out. I can see I've got a CH3, a CH2, and a CH2. So if I were to separate the molecule just there, I would get C3H7 as a fragment. For C, again, I've got CH3, CH2, CH2. So if I were to separate the molecule there, I would end up with a fragment of C3H7, and that would give me a peak at 43. If we have a look at D, it might be slightly harder to see, so I've drawn this one out as well. Okay, if I break my molecule here, I end up with 1, 2, 3 carbons and 7 hydrogens, which would give me a fragment at 43. So B, C, and D will all give you a C3H7 fragment if you break just one bond, and that fragment will give you a peak at 43. In A, no matter which bonds you break, even if you break more than one, you're not going to end up with that C3H7 fragment, so you're not going to have a peak at 43. And there are no other easy ways to get a peak at 43 without breaking multiple bonds. So your answer is going to be A. Now, I know you can get that from the mark scheme, but it also says in the mark scheme that more than half of the candidates that year got it wrong. So if you don't understand it, please message me about it, okay? Just looking at the mark scheme does not help you on multiple choice questions. Number 3, you don't want to know the ion responsible for the peak with the greatest relative intensity. So by relative intensity, they just mean the highest peak, which is here at 43, which I just read from the x-axis. Easiest thing to do is look at the ions they've given you and just see if they actually have the formula mass of 43. And you'll see that the first two don't, okay? So straight away that narrows it down between C and D, okay? They both got a mass of 43, but then you need to look at the actual structure they've given you, which I've drawn out here, and see which one of these ions is actually possible, okay? The first ion, CH3 times 2 with a CH. If I break this bond right here, I get a carbon that's bonded to 2 CH3 groups and a hydrogen, which is exactly what this fragment here depicts, okay? For D, you would need a CH3 bonded to a carbon bonded to an oxygen. I don't have a CH3 that's bonded to a carbon that's bonded to an oxygen, okay? So I've got 2 CH3s. They're each bonded to this carbon, but this carbon here that's bonded to the CH3 is not bonded to an oxygen. Therefore, this peak is not possible from the molecule that they've given you. Therefore, my answer is going to be C. Okay, question 4 is similar to question 2. You're asked which alcohol is going to have a fragment NZ is 31. So again, my formula mass is 31, and I'm asking myself what fragment might have a formula mass of 31. So the first thing I'm going to consider is what's the maximum number of carbons I could have if my formula mass is 31. So I do 31 divided by 12. That gives me room for 2 carbons, okay, 2 12s are 24, and that gives me 7 left over, which would be 7 hydrogens. Now I know straight away that that's not a thing, okay, C2H7. If you've only got 2 carbon atoms, then you've got no way of fitting 7 hydrogens around, okay? So I know straight away that C2H7 is not a fragment, and it's not going to be not going to give me a peak at 31. So my other options, as it's an alcohol, is including the OH. Okay, so my total mass of my fragment is 31. If the OH is within that fragment, then the OH has a mass of 17, 16 for the oxygen, 1 for the hydrogen. Okay, so if the OH is included, that accounts for 17, which means I've got 14 left. and 14 is enough for just one carbon with 2 hydrogens left over. So carbon will be 12, 2 hydrogens is 14, 14 and 17 for the OH will give me a formula mass of 31. And this is a common fragment. Carbon bonded to 2 hydrogens. The OH, it was bonded to something else, but you've broken that bond and it's got a positive charge. So I just need to look at these alcohols and see which one has a CH2OH. Straight away I look at D and I see it's got CH2OH. If I were to break that bond there, I'd have a fragment CH2OH, and that is going to be my answer, D. Okay. So question 5 is slightly longer. You're provided with a spectrum and you're told if it's of an alkane. Okay, and you are told that one student looked at peaks 1 and 2 and narrowed it down to 2 different alkanes, whereas the second student looked at all 3 peaks and was able to give a definite answer as to the structure. Okay, so the first thing that we're going to do is we're going to look at the molecular ion peak, which is all the way up here at 58. Okay, that tells me that the molecular mass of this alkane is 58. Because it's an alkane, we know it only contains carbons and hydrogens. So I can use this molecular mass to work out the molecular formula. So if it's got a molecular formula of 58 and it only contains carbon and hydrogen, I need to see how many carbons it can possibly contain. 58 divided by 12 is going to be 4. Okay, so 4 12s are 48, which means I've got 10 left over. That means my molecular formula is going to be C4H10, okay? And that's butane, okay? That totally fits as a general formula of an alkane, 4 carbons, 10 hydrogens. But with C4H10, there are 2 ways that you can draw this, okay? I can either draw it as a straight chain and just draw butane, that's C4H10, or I can draw it as 2-methylpropane. Both of these structures are alkanes. Both of these structures have the molecular formula C4H10. So I need to look at more than just peak 1 to figure out what the actual structure is. If I look at peak 2, the formula mass of peak 2 is 43. Now I was starting with 58 and now I've ended up with a formula of 43. So to get there, to get from your full structure to 43, you must have lost 15. And if you're losing 15 from an alkane, you are losing a CH3, okay? Carbon is 12, the 3 hydrogens bring it up to 15. So if I look at my 2 structures, is it possible to lose a CH3? The answer is yes, okay? So on my first structure, I could break this bond, I could break this bond. On my second structure, I could break any of these bonds and I'd be losing a CH3 each time. So in both structures, it's possible to lose a CH3. So just looking at the second peak doesn't clear it up and tell me which structure is correct. So I now need to look at peak 3. Peak 3 has a formula mass of 29. We've seen 29 before. It's a really common peak. Okay, if you've got a peak of 29, you have got 2 carbons and you have got 5 hydrogens. Okay, 29 divided by 12 is 24. That gives me, 29 divided by 12 is 2, okay, which gives me 2 carbons, and because that's 24, I've got 5 left over, which gives me 5 hydrogens, so C2H5. I now need to look at my structures and see which one of them can give me C2H5. So if I look at normal butane, if I break this bond here, that gives me a C2H5. It actually gives me 2 identical fragments, both of them C2H5. If I look at my 2-methylpropane, there is no way I can break this molecule that gives me a fragment of C2H5, okay? If I break this bond here, I'm left with C3H7. If I were to break this bond here, I'm left with C3H7. Even if I were to break 2 bonds, if I were to break this one and this one, I'm left with C2H4, okay? Doesn't matter how many bonds you break, you're not going to be left with a fragment of exactly C2H5. So if my structure was 2-methylpropane, this peak would not exist, okay? That tells me by looking at all 3 peaks that butane is my only possible answer. It's the only alkane with a molecular mass of 58 that can produce all 3 peaks on the mass spec, okay? It tells you the written answer on the mark scheme, but I just want everyone to be clear of why that is the written answer. I'm going to make one more video because I can't go over 15 minutes, so 7 and 8 are in the next video.